Welcome to CCSD Earth Science. This is the first video in our Geologic History unit. We're going to be taking a look at what's happened in Earth's history, and how we know the ages of things and the different sequences of events in our history of Earth. And right up here is a quote from, or a paraphrase of a quote from a geologist, James Hutton. And it says that the present is the key to the past, which basically just means things that are happening right now on Earth have happened the same way for millions and millions of years. So if we look at how things are occurring on the surface and how they're forming, they've always happened that way. And that helps us figure out what happened in Earth's history. And this whole concept is actually a big long word called Uniformitarianism, which is just that things remain the same. They happen slowly over a long period of time. So the things that we see that have formed, it's happened over a long period of time. It wasn't a quick thing that formed the different features and things that we have on Earth, like mountains and layers that have been deposited. Things that have happened in the past are happening now. Okay, so this is that same kind of idea. Things that we can see, weathering and erosion that are happening on the surface, volcanoes that are erupting as that lava cools and solidifies and becomes a rock. Those processes have always occurred, and they occurred the same way. So if we understand how those things work now, it helps us to understand how the rocks that we see were formed. Now there are two basic theories of the Earth's formation. The first one is the Evolutionary Theory, which is what we go with in science. And that says that the Earth is about 4.6 billion years old. Okay, so a huge amount of time. Then there's also the Creationism Theory, which says that the Earth is about 5,700 years old. So there's definitely a big difference in time there. And like I said, the evolutionary theory is the one that we go with in science class. How do we know the age of the rocks? There are a couple of different ways that we can figure this out. The first one is the absolute age dating, and it's like what it sounds. It's the absolute, the actual age of a rock, and there are certain processes that we'll talk about later in the unit about how we figure out those actual ages. Relative age dating is really what they started with when they were looking at the Earth's history and trying to figure out the order of events. Basically, you're just comparing rocks to each other, saying, okay, this is older, this is younger. And it's all going to depend on what's around it. It's not an actual or an exact age. Okay, so if we take, for example, Mr. Miller and I. Okay, Mr. Miller, compared to me, is much older. All right, but if you compare me to my daughter, I'm much older than my daughter. So you're comparing different things to one another, or comparing rocks to one another without giving an actual age. And I won't give you Mr. Miller's actual age. I don't want him to feel too old. All right, so what we're really going to focus on right now is the relative ages. How do we compare rocks? Because like I said, that's what we really started off with. We didn't know for sure how old things were exactly, but we could get an idea of older and younger. And the first thing right here is the law of superposition, okay, which says that the youngest rock is in the top layers and the oldest is in the bottom. So if you look at these 4 different layers of rock, or sometimes we call them strata, okay, at the bottom, that's going to be your oldest rock because it was deposited first. So this is oldest. And then over time, you had more deposition and more deposition and more deposition, and this is your youngest. Okay, because that was what was deposited most recently. It's kind of like if you look at your locker. Okay, the beginning of the year, it's empty, it's all nice and clean, and then you slowly start to deposit more and more papers and things that you've accumulated throughout the year. And by the end of the year, the most recent stuff is the stuff you've crammed in right at the top. Okay, and that's how the rock layers work also. Okay, the stuff at the bottom is the oldest, and at the top is the youngest. And that's going to be how it is most of the time. Every once in a while, rock layers will get overturned, but for the most part, you're going to see it like this, where your oldest is at the bottom, youngest is at the top. So that's one way that we can compare. Okay. Another is when you have folding or faulting that occurs within the rock, and you have to think about what happened throughout that area's history. Okay. Folds and faults can only occur after the rock has been deposited. So if you've got these 4 rock layers, those had to be there first, and then those arrows are representing pressure that's squeezing in on it, and then the layers have been folded. So you can see that layer right there, 1, is the same as that one, and then 2, 3, and 4. And I wrote them all across so that you can see that even though if you go across, okay, it doesn't look like it's lined up, it's still the same layer. It's just been deformed. And what we're going to be doing a lot of is going through and figuring out the order of events, sequencing the events in Earth's history. So if we were to look at this picture right here, 1, 2, 3, 4, okay, actually, we're going to change a couple numbers here, so hopefully you are actually listening to this. We're going to say that layers 1 through 4 were deposited, like we see here, okay? And then the 5th thing that occurred is layers 1 through 4 were folded, okay? So we have to account for that event, that folding event. And that's basically what we normally will be doing, is going through and figuring out how old or the order that the different events occurred. If you look at this one right here, okay, you can see that things are kind of offset. We don't have that before picture to look at, but you can see how they kind of look like they match up. It's just that they're offset because of this fault that happened. But if we actually numbered them, that's 1, and that's 1, they're the same layer. They were at one time sitting right next to each other. That would be 2, and that's 2. That's 3, and that's 3. Okay, so if we were to kind of describe what happened in this region, you could say that layers 1, 2, and 3 were deposited horizontally, flat. Okay, you're not going to ever see rocks deposited at an angle. Okay, when you see that they're at an angle, something happened to uplift them. All right, so those 3 layers were deposited, and then the 4th thing that happened was that layers 1 through 3 were faulted. So those were all lined up, and then they were offset somehow. Okay, and that's basically what happened here. All right, so you have to pay attention to where these faults and folds are to figure out the ages, approximate ages in an area. Something else that you'll see a lot in these pictures and diagrams of rock layers are things called igneous, intrusions, and extrusions. Okay. Basically what happens is you've got these layers that are deposited in nice horizontal layers, and what happens is magma from beneath the surface starts to push up through natural cracks in the rock. Okay, and it kind of works its way through and pushes the rock out. And if you think about what magma is like, it's very hot. Well, when something hot touches another object, it deforms it, it changes it. Okay, and that's where we get something called contact metamorphism. Okay, these little lines right here represent that this magma came through and changed all of the rock that it's touching. Okay. Now you have 2 types of ways that this can happen. You can have an intrusion, which happens beneath the surface, like you see right here. This magma came up, it filled in between this layer and this layer, and it changed all of that rock. Okay, so it never made it to the surface up here. So intrusion is inside the earth. Or you can have an extrusion, which is above the surface. It's the exterior of the earth. Okay, so it actually comes up and it flows across the surface. All right, and what happens is that comes up and it's still touching these rocks beneath the surface, and it's changing it all the way around there. You've got that, what we call contact metamorphism. But if you imagine that layer is not there, this is the surface, it cools. Okay, and it becomes solid rock. Well, then over time, this layer gets deposited on top of it, okay? And you know that that came later because it hasn't been deformed. It hasn't created any contact metamorphism. So if we went through and we labeled the order that these events or these rocks were created, that would be, in this one, that would be the oldest because it's at the bottom, and then that one is the next one. But you have to be careful. Even though as we're going up, that's next, that's not the next thing that formed. And we know that because we have that contact metamorphism. That layer was already there, okay? And then this came up through and it changed all of the rock that it's touching. So we know that that came later, okay? So those contact metamorphism lines are really important. And if we look at this one, okay, again, that bottom layer is the oldest. Then that one. Now we know that the igneous well, this would be an extrusion. This igneous rock is older than this one because there's no contact metamorphism. That was solid rock before that layer was deposited on top of it. Okay, so these can be kind of tricky. You just have to be really careful. Pay attention to the contact metamorphism lines. If you see that, you know that it changed the rock that was there, which means that rock was there to begin with. Okay, it's kind of like the faulting. You can't have rocks that have been faulted if they weren't there to begin with. Okay, so the faults are usually younger, will be younger than the rock they're cutting. Contact metamorphism is younger than the rock that it's touching. Something else that you can see that will help you figure out the age of events and the order of events are these things called unconformities. So this solid line right here is a buried gap in the rock record. Okay, this was at the surface at one time, and there was rock there. Well, through weathering and erosion, it just wiped a bunch of that rock away, and then there was more rock that was deposited on top of it. So a lot of times you're going to see kind of this wavy line, which is showing you there was something there, we're just not quite sure what. And if we go through and we find the actual age, you'll see a big jump in ages from the layer above and below. Okay, so that's what an unconformity is. And if we were to go through and actually label the order of these things here, you'd have 1, 2. That unconformity is 3, and then that top layer is 4. So it kind of helps you see that, you know, these layers or these unconformities were actually at the surface at one time. If we look at this one, this is another kind of unconformity. Notice that the layers here are tilted. So we have a lot going on here. You had 1, 2, 3. Those layers were deposited, but they were deposited horizontally. They weren't tilted when they were formed like that. So 4 is actually going to be, we'll put it right here. Maybe 4. Layers 1 through 3 tilted. Okay, that was the 4th event. Then you had your unconformity, which was 5. Put that in there. And then 6. Okay. And again, we're just basing this on the order of how things occur. You're going to have that be your first rock layer because that's at the bottom. If you imagine those layers horizontal, that would be at the bottom. Okay. But you had something there, we're just not sure what, and then more rock was deposited on top of it. So an unconformity is a buried erosional surface. Something else that we do to figure out the approximate age of different places is something called rock correlation, which is matching similar rock layers across a distance. So you are looking at the rocks in Carthage, and then we could compare them to the rocks in Watertown, and then the rocks in Sackett's Harbor, and see how they all match up without actually going to every single place between all of that huge distance. Okay? And the way that we can correlate or match up the rock layers, a lot of times we use things called index fossils, and you can also use volcanic ash, because if you think about volcanic ash, an eruption is going to produce that ash. An eruption won't last for a huge amount of time, so it helps you narrow things down to a specific time period or period of time. Index fossils are organisms that lived for a short period of time but are found across a large area. And we're going to talk more about these later, but the big thing that you need to understand is the reason they're useful is because they only lived for a little bit, but they were all over the place. So when you find one, you know, okay, it's from that particular time period, and it can really narrow things down. So rock above it or below it is going to be older or younger than that time frame. So it can really help when we're trying to match up or do rock correlation. Okay? So all of what we've talked about today is finding an approximate age, saying something is older or younger. Later on, like I said, we'll look at how do they actually know specific times and specific ages of rocks.